This week we have Jude Nelson from the Stacks Foundation, Pavitthra from Hiro, who's a distributed systems engineer, and Reed, who's also a software engineer at Hiro. Let's take it away. Thanks, everyone.
Thanks, Shannon. Awesome. So yeah, we're talking about SIP-004 today. SIP-004 is all about the materialized view and kind of these, some of the underlying data structures that make the Stacks blockchain work. And so maybe to start things off, I guess, Jude, I'm kind of curious, like, this is kind of a very high level question, but, when thinking about blockchains and data structures, like, how do you actually evaluate, what kinds of data structures are ideal for a decentralized network or a decentralized blockchain? And like, what are you looking for in a data structure for something like this?
Sure. So kind of like a grab bag of different features have to all be present. I think the first and most important feature is that whatever data structure you use to represent the materialized view of the system state, it has to be what's called an authenticated data structure. Making a data structure into an authenticated data structure isn't too difficult. It just means that if you have any sort of linkages between two different pieces of data, such as between two vertices in a graph, i.e. in a tree, you just make sure that one contains the hash of the other. If you have a designated root of your graph, i.e. the root of a tree in this case, you just make sure that root contains a hash that represents all of its connected nodes. And that's basically what a Merkle tree does. It's what, as we'll discuss, a Merkle skip list does. But generally speaking, it just means that you have a small piece of cryptographic data that whose generation is only plausibly carried out by processing a particular set of data structure properties. Like, this data structure has to have this key value pair, or it doesn't have this key value pair. Specific to blockchains, it's a bit more than that, though. In our particular case, the Stacks blockchain can fork. This is not true for all blockchains, but it is definitely true for the most popular ones like Bitcoin and Ethereum today, as well as ourselves. So what that means is that your system can have many conflicting materialized views. So if you and I see different forks, then our materialized view of the system state is going to be different. Like, I could see balances that you don't see, and you could see balances that I don't see. So whatever data structure you use to represent the materialized view, I should probably define that, a materialized view being what the state of the world is having applied all transactions. So in this case, like everyone's balances, the state of all smart contracts, stuff like that. Whatever data structure you use to represent that materialized view must be able to tolerate forks, and moreover, tolerate them cheaply, because you can make arbitrarily many forks. A third property you should have is the cost of appending or adding new data into this data structure should be cheap. And I'm talking like constant time cheap. So just because you process, 1,000 blocks or 10,000 blocks, the cost of processing block 10,001 should be just the same as processing block 1. So these constraints rule out a lot of conventional data structures. For example, you could not use you would be hard pressed to use something like a balanced search tree, for example, because the act of inserting n more nodes into a tree with n nodes already would cost n log n. Sorry, there's a fourth property here that I'm missing. The act of calculating a materialized view should be deterministic. So given the same sequence of transactions, no matter what order you get them in, but when you receive them, the materialized view you calculate should be the exact same as the one that everybody else is. So what that would mean is that the data structure you have is necessarily a history-dependent data structure. So that's not true for binary search trees, at least not all binary search trees. And that's not really true for conventional databases either. Like if you insert rows in a different order in a database, you're going to get an internal B tree structure that is different. The access could be the data is still all there, but it's the reason why, but data's still all there, but the reason the data structure is different and why it's a bad thing is that makes it that much harder to calculate an authenticated version, whereby the root hash that I calculate might represent the same data, but the hash will be different than your hash, even if you have the same data, because if you're not careful, like the insertion order is reflected in the calculation of the root hash. So not only must the data that materialized view be the same for people who see the same fork, but also the materialized view should be calculated through the same insertion order, the same processing order. Does that answer your question?
Yeah, absolutely. Pavi, you want to take it away with the follow-up question, or?
Yeah, sure. So I guess now that we kind of have an overview of like what properties we're trying to achieve, we can talk about more specifically like what we end up going with. The MARF, which is what we went with, has two data structures: the Mercallized adaptive Radix Tri, which is generated for each block, and a Mercallized skip list. So I think first let's talk about what is a tree, and how does it differ from other standard tree data structures?
Sure. So I actually don't know how you say this out loud because it's spelled T-R-I-E. I've always called them tries to distinguish them from trees. Does that work for everyone?
Yeah.
That probably sounds right. That's how I read it too.
I don't actually know how it's supposed to be said because the T-R-I-E comes from retrieval tree, so it's still pronounced like tree, but you can't really hear the I-E in English.
Right, and they're called prefix trees too, right?
Yeah, that's the other term for them. But when they were originally conceived, I'm pretty sure that's the etymology. Like TRIE comes from the TRIE and the word retrieval.
Got it.
Very cool. Okay.
Not important. So we call it regardless of how it's pronounced. The reason we went with a try is because it does have this property that it is insertion dependent. So the order in which you insert the same data will be reflected in the resulting structure of the try. And that's important because it's important. We need the data structure to reflect the same ordering of operations. We need the data structure to represent the same ordering of operations because we want to ultimately verify that you and I, if we're different peers, we see the same transactions in the same order. The second reason we went with a try, in this particular case, a hash try, is that when you insert data into a try, all it's really looking at first is prefix matching. So if you insert two keys into a try and the keys match on a certain prefix, then the path to the different values will follow the same sequence of nodes up to the prefix. In a hash try, the keys are always a cryptographic hash. So the distribution of the keys is uniform, which means that the expected depth of any value within a hash try is going to be, in expectation, it's going to be logarithmic in the number of keys inserted. So we went with a hash try specifically. Oh, sorry, and the other property you have is by using a hash try, the key size is fixed. It's the length of the hash. So what that means is what it means is that the average depth of any key value pair in the try is going to grow logarithmically with the number of keys, but that itself is bound by a constant. So you have O1 insertion time and O1 retrieval time. In fact, a lot of some programming languages, like I think Haskell does this, they use something called a hashed array mapped try to implement their hash table internally, and that's how they can get the O1 property for insertion and lookup based on the content. So that's the use of a try.
And I guess I just wanted to maybe clarify a little bit, like in addition to the try kind of having all of these good properties, like maybe Jude, you could just give like a really quick overview of like what a try actually is and like what it kind of looks like, because it is a tree in a way, but it's somewhat different from like a binary search tree.
Yeah, so here's a really simple example. In a very naive sense, and this is not how we do it, but in a very naive sense, you could take a set of strings, like let's say you have the string ABCD and ABCE, and suppose they're mapped to different values, A and B. When you insert ABCD in a trie, what you might do is you might represent each letter in that string as a node in the tree. So the root node might be A, and then it might be linked to a child B, which in turn is linked to a child C, which in turn is linked to a child D, which in turn maps to the value, which we just said was A. If I insert that key value pair into the trie, and then I insert ABCE mapped to B, the resulting structure of the trie would still have the path prefix ABC, because that's already that's in common between both keys. But now node C will have two children, one linking to D, which in turn maps to the value A, and then one linking to E, which maps to the value B.
So you're kind of saying that, like, if you were to compare it to like a hash map, let's say, where you have two keys that map to different values, where the keys are like very, very similar, kind of sharing multiple, letters, let's say, or characters, but are off by a little bit. In a hash map, you have two separate keys, and even though they're duplicated, you have to represent them twice. Whereas with the trie, you're kind of sharing part of the representation of each key because you are representing it in like this more distributed tree data structure. Is that accurate?
Yeah, I mean, in the normal case of a trie, yes. But I have to emphasize, we are using a hash trie. So in our case, the keys are always uniformly distributed, and they will be random. The property of having keys share long prefixes is that's unlikely to happen in practice, and that's a good thing, because really you want the path from the root node to the value to be as short as possible.
I see.
In fact, the odds of having a key share, n characters in a hash trie is equivalent to saying that you have found two different keys whose hashes have the same prefix, and that's very hard. Like if you're using cryptographic hash, you would need to basically guess different key value pairs to form a partial collision like that.
Got it. So not only are we using a trie, but we're using an even more specific data structure called an adaptive Radix Tri. Could you maybe build up from the trie definition to the adaptive Radix Tri?
Yeah, sure. So we have the definition of a trie, which is a prefix tree, because the keys are inserted in such a way that common prefixes share the same path in the tree. We have a hash trie where the keys happen to be hashes that are uniformly distributed. Hash tries have a bound above constant depth, and the average length of a shared prefix is going to only increase logarithmically with the number of keys inserted. And then finally, we have something called an adaptive Radix Tri, which is a data structure from, I want to say, the early 2010s, originally meant for in-memory key value stores. The property of an adaptive Radix Tri is that the number of children a node can have is not fixed. Specifically, a node can have 4 children, 16 children, 48 children, or 256 children. The rationale here is that you want to make sure that you don't have that many intermediate nodes, because those take up space. You don't want to have to you want to minimize the traversal depth to reach your values. So the reason we use an adaptive Radix Tri is because I'm getting tongue-tied. The adaptive Radix Tri helps ensure this. It ensures that the structure of your trie when you insert lots of key value pairs remains very flat, very bushy. So if you insert lots and lots of key value pairs, what ultimately happens is your root node ends up having like 256 children usually, and then maybe the next layer of nodes ended up being like either 256, maybe 48 children or something like that. And then as you descend into the trie, the next layer has more and more of these smaller radix nodes until you reach the key value pair itself. The paper that talks about adaptive radix tries is focused on providing rules for promoting tries. So if you need to insert a node that has 5 children, you would promote the node 4, the 4 children node into a 16 children node. And then, from there, a 16 children node to a 48 children node, and then from there to a 256 children node as the number of children increases. So what's ultimately happening here is the node's radix the radix of the node will only increase, and the size of the node in memory only has to increase when there's actually a need for new children.
Cool. So actually, I was going to cover the next data structure, which is Mercalli skip list, but I was thinking just to make this like a little bit less abstract for people, like, could we cover like what kind of data is stored in the Radix tries?
So anything that mutates state in the blockchain is represented in the trie. So whenever you do something like store a variable, store a data map, instantiate a smart contract, whenever you need to increment a nonce or change a balance, so whenever you happen to process a transaction, really, each of those values, because they are consensus critical values, as in it's of paramount importance that we all see those same operations in the same order, those are represented as inserts into that block's trie. So every time I process a block, I'm really building up a new trie that represents all of the new data that block, new consensus critical data that block creates.
Oh, perfect. Yeah, so with that, now we can like go into the second part of the MARF, which is the Mercalli skip list. So yeah, if you could explain that, that would be great.
Sure. So a skip list is a data structure that gives you, at least the way that we build this, it's a skip list where you start your queries from the tail of the skip list. So it gives you a logarithmic lookup. So given the tail node of the skip list, you can find any node in the list with logarithmic number of queries, logarithmic in the number of nodes of items represented in that list. And appending to the skip list is it's a logarithmic space but constant time operation. So you would every time you append to a skip list, you insert a node that references a logarithmically increasing number of prior nodes. The reason we use a skip list at all is to make it so that you can quickly query. So this is kind of getting into the context of back pointers. Very quickly, every block creates a trie of data, but a blockchain represents all of the block's trie-inserted data as they are processed through time. So if I send a transaction that gives Pavitthra 1 stacks in block 1, and then I send another transaction that gives read 1 stacks in block 2, the resulting trie at the end of block 2 has to represent both the credit to read as well as the credit to Pavitthra. So what the skip list lets us do is it provides a way of querying the existence of my transfer to Pavitthra from the block in which I sent data to read, because it is a child of the block in which I sent data to Pavitthra. And moreover, it provides a way for me to efficiently walk back arbitrarily many blocks in order to query data that an ancestor block had inserted through the processing of its transactions.
Wait, so Jude, there's a separate trie for every block? Is that accurate?
That's correct.
Okay.
Well, I should maybe qualify this a bit more. The skip list itself is meant mainly for making proofs, to prove cryptographically, like to make a Merkle proof that I gave Pavitthra 1 stacks 1 block ago. The actual query itself is a bit different, and that's what back pointers are, but we'll get to that when we get to that.
Got it. Do you think now is a good time to talk about back pointers? Maybe?
Okay, sure. So as you've asked earlier, every block produces a trie, but if you're going to look up any sort of state that happened before any sort of state that was added to the blockchain before processing the current block, or given a chain tip, how do I query some state that happened in a block that is an ancestor of the chain tip? Then you can't just use the trie by itself, because the act of producing a trie from a block is the act of just processing that block's state modifications. So what we do to address this, and this is outside of what an adaptive radix tri is and why a marf is different, because it's a forest of tries, is that there's a special type of node within a block trie called a back pointer. And what that does is it refers to the previous block in which there exists a key value pair whose state is represented in the current chain tip, but whose state was inserted in an ancestor block. So you can imagine that example I said earlier, where in block 1 I send Pavitthra 1 stacks, and then in block 2 I send read 1 stacks. How do I use the chain tip as a processing block 2 to determine that Pavitthra has 1 stacks? So what I would do is I would walk the trie from the root node, and if I'm querying, if the path I'm querying is to the state that represents Pavitthra's balance, we process the insertion of my new account balance, the one that gives read money, the one that gives read the stacks. The way in which that state is processed is such that if you walk down the path to my balance to the path where my account nonce was incremented from 0 to 1, that would necessarily take me through a back pointer where I start at the root of block 2, I walk down block 2, I find a back pointer that takes me to the very same path in block 1, which allows me to keep walking down the path in block 1 to the to my account state as it was when I had just given Pavitthra stacks. So normally when you walk a tree, and this includes prefix trees, you're just walking down from the root node to a leaf node that represents the value inserted within that trie. When we create marfs, you're not only walking down a trie, you're also shunting back to an ancestor trie, to a particular intermediate node in the ancestor trie, or you can presume walking down within that ancestor trie until you've either encountered the leaf node or another back pointer, which takes you further and further back into the chain history. But the point is, you will eventually reach a leaf node, and you will only and the act of walking to that leaf node, no matter how many back pointers you encounter, is still going to be bound above by a constant, because, as we mentioned earlier, the length of each key is bound by the cryptographic hash function used to represent it. Does that make sense?
Yeah, that makes sense. So basically, I think another helpful kind of side thing we can go into is talking about how we would build a new trie if we have a new block, right? So I mean, from what I understand is we start with the root node, and then what it does immediately is it copies it basically sets the children of the root node to back pointers to the children of the root node of the previous trie. Is that correct?
Yes, that's right. So that way, if I wanted to query state from that new block, I would hit leaves that exist in prior blocks.
Cool. And then I guess we could talk about what happens if we want to update a value, a new key value pair.
Sure. Suppose I overwrite something. This would happen with my nonce key value pair when I send read the stacks after sending Pavitthra the stacks. So what would happen is the way in which we build a block trie is a copy on write procedure, whereby the act of modifying a leaf node is the act of copying forward all of the intermediate nodes on the path to that leaf node into the current trie and inserting the new leaf value as a leaf within that current block's trie. But every time we copy a key value node, we have to make sure that any of the sibling or uncle or great uncle, etc. nodes, to make sure that the pointers that were there in the node when it was copied forward are preserved, so that I can still start from the root node of the current block's trie and reach the state at the end of the leaf nodes that those intermediate nodes ultimately represent. You could imagine a naive way of doing this. Like suppose that the act of updating my account nonce would simply be the act of copying forward all of the intermediate nodes on the path from the root node to my account nonce leaf, as well as all of the subtree that the intermediate nodes claim as their children. That would be very wasteful. That would take a lot of time. The act of producing a new block tries would become a quadratic time complexity act because you're copying forward the previous chain history in its entirety every time you append a new block. This copy on write strategy, by contrast, is a constant time operation because whenever you copy forward an intermediate node that's, represents a modification to the current state try, you are making sure that if you wanted to resolve an existing key value pair, you still have a way to do that. It's just that the path you walk from the current root node of the block follows the intermediate nodes you copied forward, but eventually it will hit a back pointer to the original copy of the intermediate node in a previous block try where you can keep walking down.
Yeah, Reed, you want to go ahead?
So I was thinking maybe we could move on to talking about the proofs, specifically the Merkle proof. So, Jude, could you tell us what is a Merkle proof, and can you remind us what they're used for in the MARF?
Sure. So the ultimate goal of having a Merkle proof is to make it so that if you aren't running a full node, but somehow you know what the current chain tip is. More on that in a sec. This is what a light client would normally be doing. If you know what the current root node is, you can use that root hash to authenticate any key value pair represented in the MARF. And that's important because that gives me a way to use my mobile phone, let's say, to query Pavitthra's account balance or my own account balance or the state of his current smart contract. So the MARF is designed in a way such that you can generate these cryptographic proofs and authenticate them using the root hash that you learn out of band. So that saves you from having to go and run a full node on your phone or a rather low power computer in this case, but it gives you a reasonable degree of confidence that the key value pair you learn from an untrusted server is the key value pair represented in the blockchain. And we can rely on the cryptographic hash function to help us here because the act of producing a proof for a key value pair that does not exist or a different key value pair is the act of breaking the hash function, which is extremely difficult and it requires a crap ton of energy or a huge scientific breakthrough, neither of which are likely to have happened.
So you're basically the proof lets you validate that the key value pair that you're interested in actually exists. Is that fair to say?
It exists and it has a certain value. So you can get proofs for all the prior values as well, but you can also get a proof that it is the current value.
Got it. And so you mentioned that this is really useful if you're interested in running a light client.
Yes.
What is a light client and why is this useful for that?
So the act of running a blockchain, no matter how you cut it, is an expensive thing because blockchains don't get smaller; they only grow. They only get more and more blocks. It's slow. They don't grow very quickly, and that's by design because it needs to be possible for people to run blockchain nodes if they want to. But keeping a blockchain node in sync is a network bandwidth intensive operation. No matter how you slice it, you're constantly downloading more blocks on a fixed cadence. It's something you might use Raspberry Pi for, or your laptop, or a dedicated home server for, but it's not something you would do on a phone, for example. It would eat your battery, and it would eat your mobile data plan. It's also not something you might be interested. It's also if you're new to a blockchain community, you would not necessarily want to go spin up a node right away because synchronizing a node could take on the order of days. So instead, what you might do is, if you just want to query your account balance or query state within the blockchain without having to trust someone else's node wholesale, you might instead install a light client for that node that lets you query the state of the blockchain without having to trust the node. So right now there does not exist a light client for Stacks, but the protocols are designed such that we could go and build one. It's just we have to get to Stacks 2.1 first. But the way in which that works in the MARF is that if you can determine the set of Bitcoin block headers, which you can, that's what Bitcoin SPV does. From there, you can determine the sequence of stacks block headers on the canonical stacks chain. And from there, you can get the root hashes of all of the block tries, and thus the state of the MARF. Once you have those sequence of hashes, i.e. the root hashes for every try in the MARF, you can use those root hashes to authenticate proofs that a particular key had a particular value, or even that it existed at all at any point in time in the system. And the way in which we build these proofs is through a composition of two types of subproofs. The first of which is pretty widely used and familiar in the space of cryptographic data structures, and that's just called a Merkle proof. So because our authenticated Radix tree is also a Merkle tree, so every intermediate node contains the hashes of its children's nodes. That means that the root of every block's try will contain the hash of all of the data that it represents. And so if I just wanted to verify, like in the last block, that I sent a transaction, or that my account balance is 3 stacks and my nonce is 4, I can do that as long as I had made that change within that block. It gets a little bit harder if I'm trying to verify that what my account balance is and what my nonce is in a previous block, because I'm not sending a transaction every block usually. I might send maybe a few a day or something like that. So most of the time, the last transaction I sent is in the past. So this is in the SIP-004, we talk about this notion of what's called a segment proof and a shunt proof. So the segment proof is the Merkle proof. So the proof that a particular key value, a particular node exists in a Merkle tree. And that's done by if I want to verify that a particular key value pair exists in a Merkle tree, I would supply that key value pair plus the hashes, not the data, but just the hashes of every intermediate node's other children. And that would let me prove that a particular leaf exists at the tips exists within a particular try. If I have that leaf and I have the root node, I can ask some other untrusted stacks blockchain peer for those intermediate hashes, and the leaf node plus those intermediate hashes must hash to the root node. So that's just verifying a particular key value pair within a block try. But as I mentioned, it's a bit harder in the case of a MARF because the key value pairs you want to authenticate may live in other tries. So when we calculate the root hash for a particular try, you're not only calculating the hash of all of the intermediate nodes and leafs that the try represents, but you're also mixing in a geometric sequence of prior ancestor block try root hashes to form a skip list node. So you can make a skip list authenticated by making it so that every time you skip through the list, I believe the nomenclature they use in skip lists is you have what are called skip list columns. You can include the hashes of all of the intermediate columns that you skip through. And it works under very similar principles to a Merkle tree. So the act of verifying a key value pair in a MARF, where you're following back pointers, is the act of verifying first a segment proof, so a proof that a particular intermediate node exists in the chain tips try, followed by a shunt proof, which is a proof that the authenticated skip list includes an ancestral block with a given try root hash. And then once you have that try root hash, you can keep walking from its intermediate node down to another segment proof until you hit another back pointer, in which case you follow the shunt proof back to its ancestor, and then you keep proceeding in that manner until you hit the leaf node.
Cool. Okay, I think what we could do is walk through just an example of using the segment proofs and shunt proofs, because I think I had one little confusion about it myself. So let's say that we are trying to basically verify one value, and then to get to that value we had to follow one back pointer. And so what we end up getting is we have this intermediate node, And through the segment proof, we basically are given the hashes of all the other children of that node, which then points to our value. So then what we do is we calculate the new hash of that node given the value hash, right? And then so now we have the hash of that node. Is that like accurate? And then given that hash, we then want to calculate the root hash of that previous block in the blockchain.
Yeah. So what a shunt proof is proving is that the ancestor block exists, and it is n blocks back in the blockchain.
Right.
Some person held that value of n. So what the authenticated skip list lets you do is it says, oh well, suppose n is like 13. Well, that is 8 blocks plus 4 blocks plus 1 block back. So in the skip list, when you calculated the skip list, the shunt proof, what you really did is you skipped through the skip list back 13 by skipping back to the block 8 blocks ago, then skipping from there to the block 4 blocks ago, and then skipping from there to the block 1 block ago. That right there, that is so each time you follow a skip in the skip list, you can construct a Merkle proof for that skip list that proves that the block that was 13 blocks ago must exist, because the hash of the node that you are skipping from authenticates all of its ancestor blocks. Much the same way that a root node of a Merkle tree authenticates all of its descendant children.
Cool. Okay, so I guess my question is, I guess maybe like the thing I'm confused by now is there's like a part of data like I'm not fully understanding. So for example, like let's say we had to skip back to get to like so in the paper there's like an example of like, okay, you had to skip back to block n minus 10, like that's where your data lives. So you have to follow the skip list to n minus 8, and then follow that again to n minus 2, and then we get to n minus 10, like that's where our data lives. So basically what I understand is like, okay, like we basically compute the hash of the node. Through that, we get the hash of the block n minus 10. Then what we do is we use that, and we basically can then get the root hash, the try hash for block n minus 8 by using the hash that we just computed for block n minus 10. So the one thing that I'm confused by is that to get the root hash of a certain block, you need the hashes of everything in the skip list. So the blocks, the hashes of n minus 1, n minus 2, etc. And you need the hash of all the children, like the hash of the root node, right? So for block n minus 8, when we're computing the root hash there, we basically use the root hash of n minus 10, which was the only thing that was missing from the shunt proof. And then how do we get the hashes of the children for block n minus 8?
Sure. So every time that we add a node into the skip list, you take the hash of its previous children, so n minus 1, and then the hash of block n minus 2, the hash of block n minus 4, the hash of block n minus 8, the hash of block n minus 16, the hash of block n minus 32, the hash of n minus 64, etc., until you either reach or you pass the genesis block. So at every block n, the hash of that block not only authenticates the hash of every try in the system not only authenticates all of the children nodes in that try, but also all of those geometric series of ancestors. Right. So if you want to prove that an ancestor exists at k blocks in the past using a segment proof, you would find the powers of 2 that sum to k. And you would, and the proof itself would fill in any of the missing hashes, any of these sibling hashes for the skip list column that includes one of those powers of 2 that sum to k. So when I authenticate n minus 10, I first find the shunt proof contains the following. it will contain the hashes of all of the, it will contain the hash of block n-8, right?
Mm-hmm.
And that hash in turn is derived from its previous children, blocks n-1, -2, -4, -8, -16, etc. So what the segment proof would then do is it would contain not only it would contain the portion of the shunt proof starting at block n-8 would contain its hash for its immediate ancestor, so -1. It would not include -2 because you already have -2. That's the n-10 we were looking for. But it would also contain 4, 8, 16, 32, etc. So that when you hash all of those together, you would get the hash of block n-8, which when you turn around and combine for the hashes, you combine with the hashes for your chain tips ancestors 1, 2, 4, and 16, 32, 64. You already have 8 because you derived from the rest of the shunt proof. All of those hashed together plus the root hash of the trie at the chain tip would equal the root hash of the Marf chain tip.
Right. Yeah. So I guess like the one thing that I'm like still confused by is like how do you get the root hashes of the children at block n-8? Is that included in like some proof?
Yeah.
About,
So
like,
the
children. Mm-hmm.
every time, so as I mentioned earlier, and we really need like a whiteboard to show this. Like,
Yeah, I know. It's like hard to explain.
It's really hard to describe this.
Yeah, it really is.
So as I mentioned earlier, you can imagine that you know how a normal Merkle tree works, right? So the hash included in the root of a Merkle tree, not even a Merkle Tri, which is a normal Merkle tree, is just the hash of its immediate children, right? Mm-hmm. And then the hashes of its children are included in the hashes of its grandchildren are used to derive the hashes of its children, et cetera, et cetera. So the root hash of a Merkle tree represents all of its lawless leaf nodes, right? Mm-hmm. With me so far?
Yeah. Yep.
Okay. Right. So if you can imagine a skip list now, the way that a skip list works is when you generate the nth node of a skip list, that node contains pointers to node n-1, node n-2, node n-4, node n-8, n-16, etc. So you can make an authenticated version of a skip list just by making it so that the skip list tail that I just described contains the hashes of its nodes n-1, -2, -4, -8, etc. And those ancestor nodes also contain the hashes of their ancestor nodes, much like how it works in a Merkle tree. Make sense so far?
Yep.
Okay. So here's the tricky part, I think. When we calculate the root hash of the Marf, not the block trie, but the Marf itself, that root hash is the hash of not only the last block's root, the last block's tries root hash, but also the skip list ancestors of that.
Right.
So the act of calculating the state root of the Marf is the act first of calculating the root hash of the last block you just processed, plus the hashes of all of its skip list ancestors.
Yeah.
So yeah, if you can imagine in three-dimensional space, like you have the trie that descends down in 2 dimensions, and then behind it you have more tries, and the root of the trie you just built not only contains pointers to its children, but also to pointers back to its geometric series of ancestors.
Yep.
Okay. And so the way in which we can calculate, the way in which we can walk back, so all the shunt and segment proofs are doing is they're just authenticating the logic, they're just authenticating the walk you would take from the tip of this Marf back to a key value pair in some ancestor trie. The segment proofs just verify the part of the path you take when you are walking down within the same trie. And the shunt proofs verify the part where you walk back to an ancestor by following the back pointer.
Jude, it would be so amazing to have like an animation visualizing this process. But the visual of it being kind of this 3D data structure where you have, where kind of extrudes backwards almost is really helpful for me, at least when I'm thinking about this. But anyway, I'm thinking maybe it's a good time to open it up to the group for questions for Jude or for any of us, I guess. Sound good?
Sounds good. Yep. Raise your hand if you have a question, and we'll bring you up on stage. Hey, Pavitthra, go ahead.
Hey, Jude. Thanks. As you were saying, I agree, like a visual aid is super useful, almost critical. I think for people who want to learn more about MARF and maybe understand the data structure a little bit, like are there resources, whether existing resources that we might have or sort of out there in the literature that people can read to deepen this understanding?
Yeah, sure. So, I mean, there's obviously the SIP-004. Beyond that, there's the ART paper, which is the Adaptive Radix Tri paper. I believe it's referenced in SIP-004. Also, there's the generic data structure called the skip list. It's not really something you normally find in a lot of programming languages as a first-class data structure, but they exist. Wikipedia has an article on it. An authenticated skip list, this is where you kind of have to start using your imagination. I'm pretty sure there's papers somewhere that describe an authenticated skip list, but it's just a natural extension of this idea of authenticate a data structure. So make it so that every node has the hashes of its children. Putting that all together, I think we submitted a patent application for that. I'm not sure if it's described anywhere else.
Cool. Well, for anyone listening, if any sort of creative visual artists out there want to take a stab at making a nice visual, either animated or static, at least Hiro would love to sponsor such an effort. So if you're interested, just send me a DM. Thanks.
Also, just to calm nerves here in case that just happened, Hiro owns the patent and it's part of the patent defense fund. So it is like the patent defense group is legally obliged to hold the patent just to prevent other people from trying to infringe upon it and then sue creators. It's not meant to be used proactively. It's kind of like Mozilla's patent defense fund. So please make derivative works. It's all good. It's GPL3.
Does anyone else have any questions?
All right. Pavi and Reed, do you have any other questions?
Yeah, I mean, we could definitely keep going. I have some more kind of higher level questions. Like, I'm curious, Jude, how unique is this kind of combination of data structures and what has been built in the Stacks blockchain? And like, was there any inspiration from kind of other projects in the crypto world? Or, is this kind of really kind of a unique combination of things?
I think the closest thing might be Ethereum's Patricia Tri. I actually was researching this back when I was building the MARF, and I couldn't really find very much good data about how their backpointer system worked. If I recall correctly, a Patricia Tri has this notion of a extension node which contains backpointers to tries from previous blocks. What was not clear to me, though, is whether or not they are structured in a way that allows for an O1 lookup of a previous value as opposed to an ON lookup or an O log n lookup. It's also not clear to me how exactly the proof system works within the Ethereum Patricia Tri. I know that it exists. It's just hard. I just couldn't find any good good documentation that describes how exactly it works. So a lot of it was just like, stabs in the dark, thinking like, oh, well, if they can do it, so can we. So let's try to make sure at least we have good asymptotic boundaries on what we're doing.
Got it. And so like the Patricia Tri wasn't something that the Ethereum project came up with, right? This like the Patricia Tri is like much older data structure.
I think I don't know where the word Patricia comes from specifically, but the notion of there being an authenticated hash trie is pretty old.
Okay. Bobby, do you have any more questions? Anyone else?
Yeah, we could talk about path compression and latency expansion with respect to the MAR.
Sure. So when building so I should probably have said this a bit earlier. When building up a prefix trie, prefix tries are almost always going to be sparse. So the number of key value pairs is going to be significantly less than the number of intermediate nodes you would need to represent them all. That poses problems for the practical implementation of tries that almost every trie implementation ends up solving in some way. How do you keep the number of intermediate nodes at a minimum? So the tactics that are generally used, and these aren't something we invented, these are described both in the art paper as well as generally in like how do you build a sparse trie, are this notion of path compression and leaf expansion. So imagine that my key is 32 bytes long, which it is in our case. If there's only like 10 key value pairs inserted into the trie, there is no reason at all why I need to make a 32 node path of intermediate nodes to my key value pair. So you could do that, and that's a naive way of doing it. Like you make each byte into its own intermediate node in the prefix tree, but why do that? Like there's unlikely to be any children that share that prefix, so the act of making that long prefix of nodes is just wasting your time and it's wasting your space. So the first optimization, leaf expansion, is the notion of only store the part of the key prefix as intermediate nodes where there are siblings or where there are cousins or second cousins or third cousins. And the part of the path that is unique, to that key value pair, you represent that portion of the path within the leaf node itself. So imagine inserting the string A, B, C, D, E, F, G when there's only 3 other key value pairs like A, B, X, 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 and A, C, Y, 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 Y. So what would happen is there would be the first node would be A, since that's shared by all 3 keys. The second node, however, could just be a leaf, and it could be B, C, D, E, F, G, H, I, J, K, because there's no other nodes that share any more of that path prefix. If I later insert a key value pair, A, B, C, D, E, Z, 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 well, now there's some path overlap between the key I just inserted and this new key. So what I would do is I would take my leaf node and I would update it so that it only contained the new unique suffix to that key value pair, and I would make a new intermediate node that contained the common intermediate portion of the path. I believe that would have been F, G, H, I, J, K, and then that descending from there would be my original key value pair and this new one that ends in Z, 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 Z. So that's leaf expansion for you. You keep the unique suffix of the path as some metadata within the leaf node, as opposed to representing it as intermediate nodes. The second technique we use, path expansion, is this notion of making it so that if you have 2 key value pairs that have a common prefix, or at least like a common segment of path, that segment of path is only represented within one intermediate node, as opposed to making it so that each portion of that key is represented as a sequence of intermediate nodes when just one would suffice. SIP-004 has diagrams that talk about this and shows how you can represent both unexpanded keys and compressed paths this way by making it so that part of the common prefix lives within one node as opposed to n nodes. And the purpose of this, again, is to make it so that you can minimize the number of intermediate nodes you need to represent all key value pairs that you insert into the block trie.
Perfect. So if anyone else has any questions, feel free to raise your hand. Other than that, Reed, do you have any other questions?
No, I think that's about covered it for me. But yeah, seriously, if anyone else has any questions, please go ahead and ask them. Super high level questions are totally fine. Really nitty gritty, low level questions. Jude is happy to answer all of them.
If no one has any other questions, I do have a nitty gritty question. And it is the same that I tried to ask before, but I didn't articulate it well. But now I think I've thought of a better way to ask the question. Okay, so here's my question. When traversing back a few nodes, right? So when we're basically trying to authenticate this proof that we received, we got a series of segment proofs and shunt proofs we're trying to authenticate. So the question I was trying to ask before was really a question of where a certain piece of data is coming from. So I know we basically have to follow the skip list to reach a prior node. So I get that. And then so in the shunt proof, for example, if we go n-8, we follow back to n-10. We basically
Other way around. We go to n-8 first.
Yeah, we go to n-8 first. Wait, what?
Sorry, keep going.
Oh, sorry. Okay, so we go to n-8, then we go to n-10. We basically start authenticating at n-10. We compute the hash for n-10. Then we basically, in the shunt proof, we basically have from block n-8, what we have are the hashes for blocks n-9. We don't have the block hash for n-10 originally, but we computed that. We have the block hash for n-12, and then so on and so forth, right? So basically, now we have the root hash for n-10. It kind of plugs into that place that of that missing data that we needed to compute the root hash for n-8. So now my question is, in order to get the root hash for n-8, not only do we need the skip list, which now we got the missing part, we also need the hashes of the children. However, I don't see anywhere in the segment proof that we get the hash of the children of block n-8. And that's what I'm confused about. How do we get the hashes of the children of that root node?
You don't need to. So what happens is that you have the segment proof that starts from the leaf node in the block that's 10 blocks back, and it goes up to the intermediate node that you would have reached by following the back pointer. With me so far?
Mm-hmm.
The back pointer just contains the hash of the ancestor block. So what you're really trying to verify is, can I walk and root forward now? Can I walk forward from this intermediate node to the same intermediate node that I would have copied forward when I produced the future block? And that's what the shunt proof lets you do. Because as you said earlier, you calculate the hash of this intermediate node here. You can verify that you don't need to verify just yet that intermediate node belongs to that particular trie, because the same exact path exists in block n from n-10. This is the way in which we copied it forward. So you can kind of imagine and this is again apologies, you kind of need a three-dimensional view of this. You start from the leaf node of block n-10, you walk up to the intermediate node, that's segment proof number 1. Then you shunt forward to block n-8,
Yep.
and then verify that n-8 is included, because that's the way that we structured the authenticated skip list. Then you shunt forward from there to block n, to its intermediate node, and then you continue to walk up block n to reach block n's root.
So yeah. So I do get that process, but we're trying to say that so in the paper it basically was okay, the first segment proof lets the client calculate the hash of the children of the art root node in block n-10, which I get. Then combined with the first part of the shunt proof yields the art root hash for n-8. So that second part, getting the art root hash for n-8, I'm still confused why we don't need the children, the hashes of the children. It seems like we're missing that. So how do we yield that root hash then?
Maybe this will help. When you walk to, when normally doing a query on the Marf, when you walk to n-10, what's really happening under the hood is the back pointer itself just contains the hash of block n minus 10. It says like, hey, like, you know, resume from the same intermediate node, but in this other block.
Yeah.
When you start working.
Yeah.
So the what we need to verify then is block n minus 10's hash is actually that.
Right.
Right. So maybe it's not too well described in the. I know the example in SIP-004 is a bit sparse. But the way, but recalling from the code, the way it works is you start from the leaf node in n minus 10. You walk up to the intermediate node that you would have jumped to from block n. You verify that the hash of block n minus 10 is what it should be by using the shunt proof.
Got it.
Where n minus 8 comes in.
Okay, so we're basically, are you saying that we're not just like recalculating the hash, the root hash of n minus 8? Like we're not like trying to get that.
No, we're not trying to get that.
No. Oh, we're not. Okay. I think the wording just confused me. Like in the paper. Okay, cool.
Yeah, we're actually given n minus 8 as part of the shunt proof, as well as given n minus 16, n minus 32.
Okay.
Because we're ultimately going to verify that the hash of block n minus 10 is what it should be.
Okay. I was under the impression that we're trying to like basically get the root hash along the way, even like for the things that we like skipped along. But we're not doing that.
Yeah, but you shouldn't need to, because the root of the marf is not the same as the root of the trie. The root of the marf is the root of the trie plus the hashes of its geometric series of ancestors.
Okay. Cool. All right. Thank you. I see you, Shannon. We're wrapping up now.
It's good. All good.
Yeah.
Loved it.
Yeah.
Yeah, we are at time. Thanks, Jude, Pavi, and Reed. That was awesome. Our next session will take place on Wednesday, June 9th at 2 p.m. Eastern. We're going to cover SIP-5 with its author, Aaron Blankstein. I'll release the recording. Sorry, I can't talk. Let me start over. I'll release the recording of this session in our Stacks YouTube channel. Thanks, everyone, for joining. Have a great rest of your week.
Thanks, Shannon. Thanks, Jude. Thanks, Pavi.
Yeah, thanks, everyone. Goodbye.